This is a finalized model, a wind tunnel model of the Nexus car, and it incorporates one of the most important things that you can model on a car, and that's the internal cooling system or internal flow. And this model incorporates a front cooling system which brings air in from the top of the car and ejects the air out the bottom of the car. So the air is actually moving past the car into the front duct, down vertically, and then out the bottom. So what we do is we place an oil cooler in that duct so that we can actually get rid of a lot of the engine heat from that oil cooler, while at the same time we can provide occupant heating through that same duct. Because we have that warm oil running through the oil cooler, we can get warm air after the air runs through the heat exchanger, and we vent that into the passenger compartment. In the summertime, mind you, we can vent all of that air downward out the side of the car, and therefore getting rid of engine heat. So that's one part of the system when it comes to the cooling system. The other half of the cooling system is back here. The way this cooling system works is we bring air in through the bottom here by a fan. We have to actually suck the air in with a fan, and then we get rid of it out the back of the car, out here and out here. And that provides engine cooling air. That's air that rushes past the engine head and the cylinder, and it's expelled out the back, and it gets rid of heat. So this model models both of those engine cooling systems, and when it's in the wind tunnel, air is actually passing through the inside of the model, passing through the cooling ducts, passing over a mock engine and a mock fan, so that we're able to predict how much of an effect that the cooling has on the car.
I think one of the things in design that's always difficult to accept that is, I guess, in order to really achieve any good design, you have to fail. And one way to achieve better and better designs is to sort of double your failure rate, if you like. And one of the things that we found out, one of the highly sort of stressed parts on our car is on the Nexus vehicle is the front suspension system. Since it's designed to be very aerodynamic and very small, as the wind would see it when it's traveling down the road, it necessarily had to be very highly stressed. And because of that, we had to go through about 4 or 5 iterations on the upper A-arm, the part we call the upper A-arm, before we actually got one that would be functional out on the road. If we could zoom in on the car here, we can see that the piece that we're actually talking about is this little unit right here. This is the upper A-arm right here, and all the weight that's acting upwards on the wheel, where the body acting downwards, is actually carried by this component right here. And although it looks very aerodynamic in this particular cross-section, this is actually what the final shape will look like, and we'll put a nice rounded nose on it and a little bit of a tail on it. The part that we see up here, if you like, is what's actually setting inside the car. All right, and this part is out in the airstream, and the actual wheel attaches on, and it would be sitting out here. One of the things we might want to look at is what would happen if we took a cross section and cut the car straight down like this. To understand where this piece really goes, if we cut the car straight down like this, we can just go up to this blueprint here for a moment and take a look at the piece we're actually looking at. And it's this piece right here, and you can see a force axe up on the wheel, and we have a shock that mounts from the top of the upper A-arm across to the other side of the wraparound bumper. It's not shown here for clarity, but you'll be able to see this in our testing jig. I'll show you in just a moment. And so there's a lot of bending that goes on in this particular member right here, and this is one of the things that causes it to fail. It pivots right at the plus sign there, if you like, and this wheel is shown in the maximum downforce or maximum bump or rebound position, and this wheel is shown in the maximum actually upright position. That's as far as our suspension can compress, and our total suspension travel between those two is about 6 inches. So we can hit about a 4-inch bump, and we can also rise, the car can actually rise up in the air about 2 inches before our wheels would come off the ground. So maybe we can just take a quick look at the test stand that we set up. I mentioned one of the things that you have to do in order to succeed in design is to fail a little bit, and maybe we'll look at some of the first marks that we tried in order to design the A-arm. This model has been tested in the jig that I'll show you in just a minute, and we can see that it has actually failed, because as we look here, we can see some light underneath here, and we can see that the skin has actually bent in the center. And this is one of the very first designs that we tried out for the A-arm. It has a weight written on here, approximately 4.13 pounds. It is a very wide, physically wide unit, and the lips that we had on the front and back were put on in the hopes that we might be able to put a nice aerodynamic rounded nose and an aerodynamic tail on the structure when we were finished. This hole in the end is just where our ball joint actually screws into. And of course the clevis on the top is where our shock will hook onto. And this particular pivot point right here is where we'd actually have some rubber grommets so that the suspension motion wouldn't cause the frame to really hammer. We'd sort of isolate the vibration at that point. We can see that this particular unit has some ovality here, and this is deemed to have failed. And this particular unit failed at about 3 times the normal weight that would act on the front wheel of a car. And we've determined from the literature that suspension components such as this should be able to last up until about 4.5 times the normal weight that would be on that particular component. So we moved into a Mark II design, if you like. We'll just put this one away for a moment.
This big piece of wood here is what we call a body buck. And what its purpose is to actually make the real full-size body. After we spent some time in the wind tunnel and come up with a model that looks like this, that we know is a good aerodynamic shape, well, we have to build that full scale. So to do that, we use a fairly standard boat building technique. We build a male plug, which this is called as a male plug, and this will be an exact replica of what the body is going to look like. What we do with this is we get it perfectly smooth, we paint it, and then we cast a mold from this body buck. And the mold is made out of fiberglass, and the fiberglass is applied to this body buck all over the place in about 5 or 6 layers. And then we separate the 2 halves. And you have the body buck and you have the mold. And it comes apart, and then you have what's called a female mold. And from that mold, we can make the actual bodies of the car by laying out fiberglass inside that mold. What this gives us is a very smooth outside surface. And the inside of the surface is actually a little bit rough, but we don't really care about that. It's the outside surface we want very smooth. So we go through this whole process of making a body buck, which is this guy, a female mold, and then we can actually turn out pieces. And it involves basically a lot of sanding, which we're doing right now, to get the thing perfectly smooth and in the exact configuration that we want it.
Yeah. Sure thing. They could hold up the steering assembly too.
You've designed this machine here to test the nose section of your car. Can you explain what this test is actually going to tell you?
The test is designed to tell me that the nose section alone can absorb all the energy from a 30-mile-per-hour collision. The way the Nexus vehicle is constructed, the frame is built very rigidly, but it has a distinct limit. And once the limit is passed in loading, the frame crumples completely. And to avoid this, we're designing a nose section that will crumple preferentially and save the frame from any excess loads. This particular design is a solid nose made of layers of polyurethane foam. The foam is used as insulation, but I found that it has very good energy absorption characteristics. So as the foam is crushed, it absorbs a lot of energy. It's a quarter scale tester. What that means is I only need 1/4 of the velocity, which is much easier to achieve than full velocity. I have a 1/4 scale model, and I have 1/4 of the mass of the car. So the hammer only weighs about 200 pounds, and it only travels at about 8 miles an hour when it strikes the plate. So in a sense, essentially it's just a swing with a big weight on it.
Are you ready to roll? There.
The only existing components that we use pertain to the powertrain. Pretty well everything, the wheels and the axles, the suspension, and the way the body goes together in the frame and all that stuff, even the brakes. Some of the brake components were off-the-shelf motorcycle components, but most of the other things were handmade, and often handmade several times in order to get something that was satisfactory. And so it involved a real major effort in terms of fabricating things in our shop. Now we're doing the analysis on the car. We're going to find out what the limits are for fuel consumption, for crash worthiness, and so on. And we expect that there will be industrial spin-offs on vehicles of this type. The university naturally isn't involved in producing consumer-type vehicles, but there's been considerable interest already shown by various companies involved in the automotive industry, and they're well aware of what's going on at our university, and I would expect that by the turn of the century you'll see all sorts of vehicles on the highway that resemble Nexus in one or more ways. I would expect we'd see a lot of three-wheel type vehicles, single passenger vehicles, and very fuel efficient.
Signal light's good. Good. Tail light's good. Brake light's good.